All right. In this video, we'll talk about reactions occurring at the molecular level. So what happens in the chemistry at the molecular level. And this lecture is based off this textbook by James Rawlings and John Eckert. Okay, so to motivate this, let's consider a simple reaction. So the reaction here, we have SiH4 plus SiH2 goes back and forth to Si2H6. So this is a step in a chemical vapor deposition process. And so let's draw this up. Okay, so we have this SiH2 species, and I'm going to kind of draw it as a sphere, or I guess in this two-dimensional representation as a circle. And then I have an SiH4 species, and I'm going to draw that also as a circle. And so these things combine, and what's going to happen is that they're going to form this Si, and that's kind of poorly drawn, so let me redo that. Si2H6 species. And we'll also draw this as a roundish shape. All right, so if we want to think about the rate of this reaction, so we're going to base this on the extent of reaction. I'm going to call the extent Z, so lowercase Greek letter Z. That's this squiggly piece right here. The extent of reaction keeps track of the number of times this reaction event occurs. So when I say this reaction event, I mean this SiH2 combining with this SiH4 to form this Si2H6. So what it's doing is it's counting the number of times an SiH4 molecule combines with an SiH2 molecule and forms an Si2H6 molecule. So it's basically counting these molecular events. The rate of this reaction is then related to this extent. So the rate of reaction is going to be the change in Z divided by the change of T in T, and then that's going to be normalized by the system volume. So here, our change in T is going to be small. And when I say small, I mean like really small. So reactions at the molecular level take place on the order of somewhere between femto and picoseconds, so 10 to the minus 15 to 10 to the minus 12 seconds. So they are very fast by our standards, although some reactions are not super fast by reaction standards. So when I say T is small, it's going to be smaller than that. Or when I say delta T is small, it's going to be smaller than that. So, we'll say less than maybe 10 to the 13 seconds, and maybe several orders of magnitude less than that. So V is volume, and volume, on the other hand, it also has some constraints here. So thinking about the molecular level, if I go back up here to this drawing, the volume must be large enough that I can fit multiple molecules in it, right? So if I draw my system volume, and let me get a different color here. If I draw my system volume to be like this, I have all I really have there is one SiH2 molecule. And in this drawing, I have part of an SiH4, but in reality, two molecules would not sit like that. That's a violation of quantum mechanics. I guess unless they were tethered to a catalyst surface, maybe. But so I need to make my volume large enough that I have multiple molecules, and really what I need is I need my volume to be large enough that the fact that these are individual molecules doesn't matter. So I need somewhat of a large volume. But my volume can't be so large that I don't have good mixing, because if I need good mixing in order to explain a reaction rate based on a particular volume. So if I can't explain my reaction rate for a particular volume because the volume's too large and I have concentration gradients going on, that means that really what I have is the rate is going to be a function of the system volume because of these gradients. So if I want to talk about the rate of this reaction within a volume, that volume has to be well mixed. So V has to be large enough that the molecular representation is not apparent. We'll say, or in other words, it must comprise multiple molecules. And by multiple, I don't just mean 2 or 3, I mean a lot. And it must be small enough that, we'll say, the well mixing assumption is valid. Okay, so going back to this extent of reaction, if this delta Z term is positive, that means the reaction proceeds in the forward direction. And if it is negative, that means that the reaction proceeds in the reverse direction. If the reaction is in equilibrium, and this is a typo here, we'll say the reaction is in equilibrium, then delta Z is going to be equal to 0. And what this means is that there are an equal number of forward and reverse events. So we'll say this implies equal number of forward and reverse events. So for this reaction, note that it's easy to link the rate of reaction to the rates of generation or consumption of the different reactant and product species. So the rate of this reaction, that's going to be equal to the rate of consumption of the SiH4 species. It's going to be equal to the rate of consumption of the SiH2 species, and it's going to be equal to the rate of generation of the Si2H6 species. That's because that's all that's going on in this reaction, right? Those two species are combining, so SiH4 and SiH2 are combining to form Si2H6. That's all there is to the reaction. And then furthermore, the stoichiometric coefficients on all species are equal to 1. Because of that, we can measure the reaction rate or the rate for this reaction based on the species concentrations. So we can measure the reaction rate based on a change in species concentrations. So for example, and I guess I should say concentrations or molar amounts. And so we can say, for example, 1 divided by volume dz dt is going to be proportional to dCj dt. So This is true for the simple reaction. However, for most reactions, it is not possible to measure the reaction rate. So at least not explicitly. So we can't measure the reaction rate for most reactions explicitly. We hence must measure the rates of generation or consumption of individual species. This is why rates are often written in terms of, when we see rates, this is why they're often written in terms of specific reactant or product species. So I think here I need to delete that and say this should be consumption. And we often write rates in terms of specific reactant or product species. So for the general example, if we have a reaction A plus B goes to C, we typically are going to write the rate minus RA is going to be equal to KA, and then times some function of concentrations of the different species. So we're talking there about the rate of consumption of species A, and we're using that as a surrogate for the reaction rate because we can measure the rate of consumption of A through either the molar amount or the concentration of A, but we cannot measure, for this particular reaction, we cannot measure the molecular events. So an example of such a reaction where this is true is the NO oxidation reaction. So this reaction, 2NO plus O2 goes to 2NO2. So for example, here we can't measure the reaction rate. So the reaction here involves two nitric oxide molecules combining with one molecular oxygen molecule, and we can't track how that happens. We can't see the molecular level, so we can't sit here and count every time that event happens. And in fact, I'll show in a second that that particular event probably doesn't actually really happen. So even if we could see the molecular level, we would never see that. What we can see, though, are the rates of generation and consumption of the different species. So we can use those as surrogates for the reaction rate. So we can say the rate of reaction is going to be equal to the rate of consumption of nitric oxide, which would be equal to 2 times the rate of molecular oxygen, which would be equal to, that would be the rate of consumption of molecular oxygen, or which would be equal to the rate of generation of nitrogen dioxide. So let's unpack this a little bit, this nitric oxide oxidation reaction. So could this reaction occur as a molecular event? So the first reaction we saw here was SiH4 plus SiH2 going to Si2H6, and we basically were able to draw how that could happen as a molecular event. Well, what about this reaction, nitric oxide oxidation? Could that happen as a molecular event? So let's answer this question by considering what must happen on the molecular level for the reaction to occur. So one thing that must happen, an oxygen-oxygen bond must break. So the O2 molecule must break. Another thing that must happen is that 2 oxygen-nitric oxygen bonds must form. So how are those things going to happen? So we've learned that reactions can happen in different phases. Reactions can be gas phase reactions. Reactions can be liquid phase reactions. You can have homogeneous reactions where everything is in the same phase. You can have heterogeneous reactions where, for example, the reactant or the reactant and product species are in a gas or liquid phase, but there's a catalyst, so the reaction chemistry is occurring on a solid phase or an adsorbed phase. We'll see more on that in just a second. Right now, let's consider a homogeneous gas phase reaction. So, if you want to think about an example of that, think about the room you're sitting in and the air in the room. So we know that those gas phase molecules they're not sitting still, they are moving around very quickly. They are translating, which means they're moving in space, their center of mass is moving in space. They're also rotating. They're also vibrating. We're going to be concerned here with the translations and the rotations, and particularly the translations. So let me draw that out. So I have these molecules, and right now I'm just kind of drawing circles or spheres, and I'm just kind of randomly putting them places. And they're zooming around the room in this air, or the air in this room is an ideal gas. These molecules are zooming around in pretty much random directions. They have really no cognizance or they don't perceive any of the other molecules in the room. So they're in their eyes, and the eyes of any individual molecule, that molecule is isolated from everything else. And it's moving very fast at some speed that we could calculate, but I'm not going to do that right now. Okay, so for this nitric oxide oxidation reaction to happen in a homogeneous gas phase environment, what has to happen is that two nitric oxide molecules would have to combine with a molecular oxygen molecule, like pretty much simultaneously. So what would have to happen is I have an NO, and it's translating, and I have an O2, and it's also translating, and it just happens to be moving towards this, where this NO is about to come into, and then we also have another NO, and it's translating. And so basically I have all these molecules, they're moving around very fast, random directions. It's an ideal gas condition, so each one of these molecules is far enough away from other molecules that they don't perceive each other. But I'm going to get this coincidental event that's going to happen. These things are all going to combine or collide. We'll say boom. I don't really think they make a noise, but I can't hear on the molecular level, so you never know. This is highly unlikely. This is what we call a termolecular reaction. So for this reaction to happen, you'd have to have three molecules combine at the same time. It's pretty unlikely. And not only do these molecules have to combine, but it's not like they can just combine and form a new species. What they have to do is combine, and then that oxygen-oxygen bond has to break, and then that would form two species, two nitric oxide molecules. So for that to happen, you would also have to have some perfect orientation that would allow that bond to break and these other two bonds to simultaneously form. So it's not even the probability that they combine, it's the probability they combine in some very perfect orientation. I'd actually be curious. It would be cool to know if that has ever happened. I would guess that somewhere in the universe it probably has. But, it's a very rare event and virtually imperceptible. All right, so let's make this a little bit easier, or let's attempt as a thought experiment to make it a little bit easier. And now this same gas phase reaction is going to happen over a catalyst surface. So I'm going to draw a catalyst surface here. And again, then we have like these molecules, and they're kind of randomly placed, and they're moving around at random speeds and directions. This molecule here looks like maybe it could come into contact with the catalyst surface that's kind of translating towards there. So let's say that it does that. So this molecule is going to actually hit the catalyst surface, and we'll say boom. And so then what this is going to do, let's say this is an oxygen molecule. Now it's bound to the catalyst surface. So this is our catalyst surface. That's pretty poorly drawn, but I'm just going to leave it that way. This right here is a bond that I drew between the molecule and the catalyst surface, just for illustrative purposes. Okay, so now I have this oxygen molecule on the catalyst surface. And so now if I had a gas phase, what I would need to do here is basically two NO molecules would have to collide with this oxygen molecule. Maybe this is a little bit easier than the last case due to the fact that this oxygen molecule is stuck to the surface, but still this is going to be a pretty rare event. I would have to get this oxygen molecule to bind to the surface. It would have to stay there. It would have to be there long enough for the nitric oxide molecules to collide with it. And again, we'd have to get some very perfect circumstance where those two nitric oxide molecules collided with it at the very same time, right? So if they collide in sequence. If one collides first and starts a reaction event, then I can't get this single molecular event to happen. So they would have to collide at the very same time, and this is still very unlikely. So to answer our question, no, this reaction is not likely to happen as a molecular event or a single molecular event because the likelihood of 3 molecules colliding let alone at an orientation that would favor a reaction, and let's say favor bond breaking and forming, is tiny, minuscule, negligibly small. All right. So now let's go back. So we've seen 2 examples of reactions. We've looked at this SiH4 plus SiH2 goes back and forth to Si2H6, and we've seen this nitric oxide oxidation reaction, 2NO2 plus O2 goes back and forth to 2NO2. What if I told you that the rates for these reactions both followed elementary kinetics? So the rate of formation of Si2H6 is equal to rate constant times the concentration of SiH4 times the concentration of SiH2. And also, what if I told you that the rate of NO2 formation is equal to a rate constant times the concentration of NO squared times the concentration of O2? So what if I told you those 2 things, and I said that the first reaction is elementary, but the second one is not? Okay, so mark this as, times my teacher lied to me. So I'm not lying to you now, but I was hiding the truth earlier when we would classify reactions as elementary based solely on their reaction rate. And I'll get to why in just a second. So when we write a chemical reaction, so a reaction, I should say here, such as A plus B goes to C plus D. And in fact, let me write it even more generally than that. Let me write AA plus B, B plus C, C plus D, D, where the lowercase letters are stoichiometric coefficients and the uppercase letters are species. These tend to convey 2 different meanings. The first meaning is probably the one that we're familiar with. That's the change in the relative amounts of species that is observed when a reaction proceeds. So in this particular reaction, what that is saying is that AA molecules are going to react with BB molecules to form CC molecules and DD molecules. So we'll say the change in the relative amounts of species that is observed when a reaction proceeds. The other thing that is conveyed by a reaction is the actual molecular events that happen as this reaction proceeds. So when we're talking about the first reaction that we looked at, the SiH4 plus SiH2 goes to Si2H6, that is a statement of both of these things, the relative change, or the change in the relative amounts of the species that's observed as the reaction goes on, and also the actual molecular event that occurs. In the second case, nitric oxide oxidation, that tells us the relative changes in the amounts of the different species as the reaction proceeds, but it's not telling us about the actual molecular events. It's only telling us about the change in stoichiometry, or the stoichiometry needed for the reaction. And so what we do is we call this first piece that is the reaction, or this definition here, basically, what we call that is a stoichiometry statement. And then the second one is an elementary reaction. So the true definition of an elementary reaction is a reaction that happens at the molecular level, and it can basically proceed from reactants to products without the need to form intermediate species. So we'll say an elementary reaction is, let me write it a little differently. So let's say a reaction that proceeds at the molecular level and can proceed without the need to form or to pass through, let's say both, form or pass through intermediate species. So an elementary reaction goes directly from reactants to products. There's no need to form any intermediate species. So if we go back to this nitric oxide oxidation reaction, for that reaction to happen, we have to have a molecular oxygen bond must break, and then two oxygen nitric oxide bonds must form, right? So when the oxygen-oxygen bond breaks, for example, that forms oxygen atoms. Those oxygen atoms are intermediate species. By intermediate, I mean they happen on the route from reactants to products, or they're species that come about as the reaction proceeds from reactants to products, but they are not part of the overall reaction. So the overall reaction only involves two nitric oxide molecules, one molecular oxygen molecule, and two nitrogen dioxide molecules. It doesn't involve any oxygen atoms. Those oxygen atoms are intermediate species. So elementary reactions are usually unimolecular or bimolecular because the probability of species coming into contact decreases as the number of species increases. What I mean by this, it's a lot less likely for a termolecular reaction to be elementary than it is for a bimolecular or unimolecular. If the rate of a non-elementary reaction happens to exhibit elementary kinetics, it is purely coincidental. So if we go back to this nitric oxide oxidation reaction, we said that the rate was going to be the rate of generation of NO2 is going to be equal to a rate constant times the concentration of NO squared times the concentration of molecular oxygen. This means that the reaction under whatever conditions this rate law is true, this means that this reaction is exhibiting elementary kinetics. So it exhibits elementary kinetics. However, it is not an elementary reaction since it cannot proceed as a single molecular event. In other words, the fact that it exhibits elementary kinetics is purely coincidental. The way this reaction proceeds, it is likely via a reaction mechanism. And the reaction mechanism is then going to be comprised of multiple elementary steps. So if we consider the case where this nitric oxide oxidation reaction is happening over a catalyst surface, one possible reaction mechanism is written here. In this notation, I've written catalyst sites, or I've denoted them with an asterisk. So this asterisk is an open catalyst site. If I have a species with an asterisk next to it, that means it's bound to the catalyst. So if I wanted to draw that, an open site would be, so this is the catalyst surface. And I have this bond here, kind of where a molecule could sit, but I don't have any molecules sitting in it. That could be an open site. And then if I had NO star, that's going to be, I have NO bound to the catalyst. So this is also catalyst surface. Okay, so I've got my steps here. First reaction is going to be a gas phase nitric oxide molecule reacting with the catalyst surface and becoming bound. My second step is a gas phase molecular oxygen molecule reacting with the catalyst surface becoming bound. I then have my bound molecular oxygen molecule reacting with another site on the surface to form two oxygen atoms. I then have nitric oxide bound to the surface and an oxygen atom bound to the surface reacting to form nitrogen dioxide bound to the surface. When I do this, I free up a site, so a site becomes free, or I regenerate a free site. And then in my last reaction, I have nitrogen dioxide, which is bound to the surface, desorbing. So it becomes unattached from the catalyst surface and regenerates another catalyst site. So the overall reaction, typo there again, the overall reaction 2NO plus O2 goes to 2NO2 is going to be a linear combination of steps 1 through 5. And the overall stoichiometry is reproduced by adding 2 times our reaction 1 plus reaction 2, so 1 times reaction 2, plus reaction 3, plus 2 times reaction 4, plus 2 times reaction 5. And I can turn this into a vector, which is, it's useful to do when we study reaction mechanisms. The mechanism that we're looking at right now is pretty simple. It's only got 5 steps. But in general, reaction mechanisms can have many reactions. So it becomes useful to look at these or manipulate these in terms of vectors. If I do that, I'm going to call this vector 1. I'm going to have 5 entries, 1 for reaction 1, another for reaction 2, reaction 3, reaction 4, reaction 5. And I can just put here the numbers I would need to create a linear combination of those reactions in order to recover my overall reaction stoichiometry. I can then write the stoichiometry matrix for the reaction mechanism. So I'm going to call that the Greek letter nu. I'm going to need quite a large matrix, and I want to actually move this over because I have a lot of species. Okay, so now I'm going to make slots for all of my different species. I have my NO gas, I have my NO star. All these asterisk species, those are the ones bound to the catalyst. All those are intermediates, so those do not show up in the overall reaction. The only species that show up are gaseous nitric oxide, gaseous molecular oxygen, and gaseous nitrogen dioxide. All other species, all of the ones with stars, including the free site, those are all intermediate species. But I still need to account for all of them in my stoichiometry matrix. Right now I'm defining what the order of species in my stoichiometry matrix should be. And once I define this, I'm going to stick with it. I can give myself just a little more room here. Okay, so now I can take my different reactions. I have 5 reactions, so I'm going to have 5 rows in this matrix. I have 1, 2, 3, 4, 5, 6, 7, 8 species, so I'm going to have 8 columns. Of these, this, 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 and this, those are all my intermediate species. So I need a lot of intermediate species for the overall reaction to occur, which means that it cannot be elementary. The overall reaction is not elementary. Okay, so now let's fill in the stoichiometry matrix. Note that I don't have to, as I write the stoichiometry matrix, I do not have to scale the stoichiometry of any of those steps. This is because those are all elementary reactions. So the rate of each of one of those reactions is going to be, I can determine that based on the rate of generation or consumption of the different species. So I don't need to do any scaling here. All right, so that's my stoichiometry matrix. If I then take this vector S and I multiply this by nu, so I have a 1 by 5 matrix and then a 5 by 8 matrix. So if I multiply S by nu, I will get a 1 by 8 matrix. That is going to give me the statement, the stoichiometry statement that I started out with. So that's going to be, if I take my final, if I do this multiplication, I can take my same order of species here. I'm going to get myself in the firm again, which I don't really need room over here, so let me scoot it over. And I should get -2, 0, -1, 0, 2, 0, 0. So this is my overall stoichiometry. I have a -2 for NO, I have a -1 for O2, and I have a +2 for NO2. This gives me the overall reaction, 2NO plus O2 goes to 2NO2. That's the overall reaction I'm looking at. And then notice also that the values for each one of the intermediate species go to 0. That's because those don't participate in the overall reaction. Those are intermediate species. They participate in the steps, but if your reaction mechanism is consistent and complete, that would mean that all of the stoichiometric coefficients of the intermediate species would cancel out, so that the overall reaction is this gas phase reaction here.